So this video will have a number of short videos embedded in the slides. So occasionally I'll just click those through. They're mostly for your entertainment. Hi, my name is Christien Rioux. I'm the chief scientist and co-founder of Veracode. We are a company that specializes in automating static analysis of binaries and solving the sort of application security in the cloud problem for people. If you're writing software or buying software, it's the kind of thing that we've developed to help you analyze these programs. So I'm going to focus today on the first half of our analysis process, which you can think of it as two parts. You can think of it as modeling a binary that is, either sent to you across the internet or something that you find on a web server. Use your imagination about where you get the binary, but modeling that and decompiling it to a point where it is semantically understandable by a human being or by an automated scripting system that can analyze and use data flow and control flow to actually search that program for characteristics or flaws or quality problems or whatever you actually want to do. So basically you have a modeling process and a scanning process. And the modeling process really isn't security specific so much. It's really mostly reverse engineering. The security part would be the scanning that you do with that model afterwards. So we're going to get into the details of how the model is built here. I'm not going to get into the details of how the scanning happens, though I can be applied for details if people are really interested after this. We can talk about it over lunch. So this can be a 2-hour session, so this would be a good time to use the restroom if you have to. But all right, I'm just going to start here. So, okay, so the entire presentation is going to take an Intel 32-bit view of the world, just for simplification. All of the techniques that are being described here are applicable to ARM platforms and Spark and Ruby and all of these other things that are not even binaries. Basically you have, when you design a system like this, you have a lot of choices to make. I chose to make the system retargetable and resourceable, which meant that I had the ability to take an arbitrary platform binaries on the input and produce arbitrary source code or scannable output on the output. In the middle, I have a single intermediate representation that I get to manipulate that transforms the thing from a low-level representation into a high-level representation. Now, if you're taking in something like, say, Ruby, you're not going to be doing this kind of process. You're going to be doing a very different kind of process, but it's the difference between compilation and decompilation. We're going to focus on the decompilation pipeline. We're also going to be taking a C++ bias in the slides today. Java is very much an easier decompilation pipeline. It has the unique property of being verifiable, which gives you many qualities that make decompilation easier, like if you have a use of a variable at a particular spot, you have a guarantee of its type based off of the path that it that you've taken through the stack to get that variable in the stack. There are many characteristics of verifiability that make decompilation a lot easier. C++ actually has very few guarantees, but there are some that come from the compiler, and we'll talk about those because they're actually very salient. They're very important to the actual understanding how decompilation is possible at all. C#, very similar to Java. So the research here has taken me about 5 years to develop and about 5 more to get right in terms of implementation. So it is kind of a hard thing to do. Hopefully the slides here would save you some time if you decide to get started or to build off of others' work. I've got some advice. If you were going to start, I'd start with LLVM's IR. It's pretty good, but we're going to get into maybe why you might want to design your own IR. Yes, there are patents involved here. I've done some work that I believe is unique and protectable, but we are not going to be talking about any trade secret type stuff, but we will be describing the sort of patent-pended stuff in detail, as well as a whole bunch of things that are not even patented. So feel free to do whatever you'd like. But the binary modeler and the intermediate representation and the querying system are effectively the 3 major parts that come together here. The modeler has as its inputs a binary and all of its dependencies, potentially symbols and other development files that you may have laying around, anything that you're able to collect from about the program, and basically a set of environment information. And environment information is things like a description of all of the Windows headers. In Win32, you'd have all of your DLLs and then all of the header files in the Windows SDK. That is a whole bunch of things you're not going to be decompiling. We concern ourselves with an IR. An intermediate representation means different things to different people. In many compilers, you'll see that there are many different kinds of IRs. You'll see abstraction stack trees, register transfer languages, single static assignment trees. If anyone's ripped into the GCC source code at all, you'll see all of those different things as different phases in the compiler. I've chosen a single IR that is capable of representing low-level and high-level semantics. That way, I have the ability to represent both at the same time during the decompilation process. This gives me a number of unique characteristics that I'll get to. There are a number of other IRs out there that I considered, including things like Spark and Score, Pegasus, and REIL came along after I got started. So there are other IRs out there that people use, and I'm sure some of the transformation pipelines that you'll see for even things like IDA Pro, they'll have some level of IR, and there are a number of libraries for Python and things that are used for program analysis that have IR components to them. So you'll see a lot of that. Designing the IR is basically the most important part of the whole decompilation pipeline. If you don't do this correctly, you're going to find that you're stumbling over your own shoes all the time while you're decompiling. You do not want to pick up somebody else's IR, honestly. You want to think about what decompilation means, and you really want to be looking to build an IR that is intended to be transformable, and you want to be optimizing this for memory usage. The programs that you're analyzing are not going to be toy programs. These are sometimes 2 gigabytes of binary with like 200 DLLs. If you're going to be analyzing that, you may need a machine with 128 gigs of memory, but if you don't design your IR correctly, you will not even be able to do it with that. So consider what it would mean to design it in a very tight, optimized form. I would not choose MySQL or something to store your IR. You look at a very, very tight, 16 bytes per object kind of representation. Designable characteristics, attention to size and speed, debuggability and readability. You're going to be constantly wondering what the heck your output means if you do not make it debuggable. Try to ensure that everything in the intermediate representation has a textual representation that is unique and obvious, so that when you're looking at it, you can debug the thing. You're going to be considering complete language support. You need to do every language element. If you miss something like you're not supporting exception handling, you will be losing out on almost everything in any major modern program. So you can't get away with just getting halfway there. You will not have a meaningful decompilation unless you support every language element that the program was built with was supported supported initially. Expect to be supporting type information and debug information. These are excellent ways to get to sort of prop up your decompiler when it can't generate these things on its own. If for some reason your decompiler cannot reconstruct structure information, you may be able to get some of that out of PDB files for the time being, until later on when you write the code that does structure handling. So effectively, being able to crutch on debug symbols has been one of the reasons why we have at Veracode been able to get to where we are, because we didn't have to have everything at once. You'll find that the number one thing you find when writing a decompiler is that you kind of need to have everything before everything else. It's very cyclical, and everything just you always find that you need to have that thing earlier on in the process. If you can just shortcut it all with having the type information ahead of time, this lets you incrementally remove your dependence on type information, and then eventually, if you don't need it, you just don't use it. but at least it gives you a crutch, a framework to get started. So the other thing is that you're going to be looking at a superset of all languages. You're going to want something that can represent namespaces and templates and classes and objects and procedures and exception handling and every kind of statement and expression, all the different things for all the different languages like C# and C++ and .NET and Java, whatever. All the different parts of all these different languages need to be representable, and they should be representable uniquely. Effectively, there should be no two ways to represent the same thing. If you have a 32-bit 0 constant number, it should be different from the 8-bit 0 constant number, but it should not be different. It should be not different from any other 32-bit 0 constant number. They should all be the same and uniquely identifiable. So that way, it's really easy to compare things like expressions if there's no two ways of representing the same thing. So consider unique semantics as well. So why a single uniform IR? And this is like the one thing that caused me to throw away 3 years of my work, is you're going to discover that as you go, that you don't know where all the code is in the program. You're going to find that you have jumps that go to registers, and you have maybe a call to the dereference of a memory expression, and you're not sure where all the control flow is. And in fact, you're not even sure if everything in the code section is actually code or if it's data or not. Separating out what's code and what's data is really dependent on your analysis of what the code that you've looked at so far means. So if you were to just kind of walk your program counter forward, from the beginning of the program at the entry point and just kind of walk down all the different paths that the program could take, you're going to hit a bunch of places where you just don't know where it goes. At that point, it's okay to stop and ask yourself, okay, let's just transform what we have. And then, we'll come back and add more code later. This means in order to do that, you have to reconstruct type information, because that's what the compiler knew about at the point that those indirect control flow operations happened. So you have a jump or a call to an indirect address. A jump is usually a switch statement, but that's usually easier to handle. But a call to like an address, like an EAX or the dereference of EAX +4 or something, to understand where that goes or how it goes to its potential targets, you need to understand the type information of the object that is being represented by that dereference. So you're going to end up having to do the decompilation of everything that you found before you can go do more code discovery and find where those call targets go. So you can't find all of the code and then do the decompilation. You have to find the code, decompile, and then say, hey, look, now that I've got more type information, I can figure out where these targets are going, and then kind of feed it all back to the beginning. Now, if your intermediate representation, if you use multiple IRs in the process, you will have thrown away the process at the beginning. You'll have thrown away the first IR and built a really complex high-level IR. And then you'll discover that you need to go back and add more low-level stuff. Now that you found you can't do it anymore, because your high-level IR that you're using can't represent the low-level semantics anymore. So what you want is an IR that can represent low-level and high-level things at the same time. Otherwise, you're going to be constantly throwing away your work and going back to the old IR all the time. This means that entire transformation pipeline, if you do it, maybe 300 times because of the level of depth of a call stack in a really complex program, you're going to end up regenerating those decompilations 300 times more than necessary if you don't use a single uniform intermediate representation. So the IR itself should look like a tree with internal linkage, and it should be a direct parent-to-child relationship. This allows language elements to contain other language elements and refer to elements via pointer or ID, minimizing duplication. The idea here is that you have a tree of things like namespaces, which contain other things. The namespaces, these scoped objects, are things that contain other things. So namespaces could contain classes, and classes can contain objects and procedures and things. Procedures could contain statements, and those can have expressions in them, and those can have internal references to variables, which are somewhere else. So the idea here is that this tree represents the semantics of the program. This is what your compiler internally represents the program as anyway. So it would make sense that you're trying to represent that and reconstruct that hierarchy. So the representation you choose needs to be able to be a hierarchical model. So I use a tree model with internal linkage. The low-level language elements you're going to see are going to be things like registers and flags, sequences, which are basically containers, expressions, statements, low-level data types and data formats, and idiomatic operations that you'll find that the CPU uses that are harder to explain. Things like block copies and indexing, and which are indexing is taking a series of bits out of a larger series of bits. Very common operation like an array index will do that, but also like taking a bit field out from a structure will also be the same kind of index. So we try to not have multiple different ways of representing an operation like that when it's really just taking a bunch of bits out of another bunch of bits. Recall, return, semantics, and all of those kinds of things that you'll find at the low level also need to be representable. The high-level language elements are going to be things like types, objects, namespaces, and templates. Templates are actually more useful than you think. I use them all the time in my low-level representations. I make templates for things like span of bits, and then I make integers that derive from span of bits, and then signed integers that derive from integers, and unsigned integers that derive from integers, and then floats that derive from spans, and that kind of thing. And that way I can template on the number of bits. This gives me the ability to have a unique identifier for int 32 versus int 8. You don't have to say that it's an int and then, somewhere magically pass around some extra stuff about how wide the int is. You just use a template to specify that. It gives you the ability to refer to each object with a unique identifier. I can just use a unique ID for every single element in the entire system by doing it this way. Let's see here. I'm visually, this is kind of how I think about it. Namespaces with classes and procedures. I tried to sort of explain that earlier. This is sort of how it looks to me. But I'll move on there. Expressions and statements. Basically, statements are sequentially executed pieces of code. You're going to find that these are evaluations of operations, calls to other procedures, returns statements, traps and trap returns, throws, exception throws, loops, switches, if-else statements, that kind of thing. So those kinds of statements are really control flow. I think of them that way. Expressions are hierarchical and really represent arithmetic and perform data flow operations. So it would be like A plus B, or A plus B plus foo of 3 is an expression. So immediates, operations, object references, things like that. So I think of expressions as sort of like algebraic almost in nature. They're transformable algebraic expressions that represent, like, if you say A plus 3, that's an expression. A is also an expression, 3 is an expression, plus is an expression. Putting them all together, A plus 3 is an expression. Taking all of that and passing it into an eval statement that has a set operation, x equals A plus 3, would be putting it into a statement that is, at that point, sort of an indivisible thing, and you could kind of move that statement around inside the sequence. Those kinds of structures are the way I'm thinking about the lowest parts of the hierarchy. So you can see things like int 8, int 32, add, etc. Even things like taking the address of another thing. Those things are all operations, and those things are all expressions in some way. So, click here. Oops, come on. Get my little head here. Statements. I'm just going to skip through these, but statements. You can think of some statements as sort of high level in nature, like switch statements. You might think of as high level, but and call statements are kind of low level, because part of the whole decompilation process can be transforming those low level call statements to high level expressions. If you have a call to an address, it's not the same as foo passing in the number 3. It's not as high level as a procedure call. the low-level notion of a CPU call where it pushes some EIP onto the stack and does some stack arithmetic, and then expects another return statement later. All of that is very low-level, but the high-level concept of a function call is what you really want to be transforming those calls to. So I keep them separate and distinct. Okay, so namespaces and sequences are really ordered and unordered collections. The namespaces are used to keep collections of objects in an unordered fashion. It's just a set of stuff. It's not in any particular order. It's just that a namespace like std would be the C++ standard template library's namespace. The C++ namespace concept is also generics in Java and this sort of the same kinds of things in C# and other. You can use namespaces as a sort of general utility to group objects. I use them also to represent collections of stuff that come from a particular image, like something that comes from an executable, and then another thing that comes from a DLL, and then another thing that comes from another DLL, or then something that comes from the Windows headers. They all maybe are in different namespaces, some of which are anonymous and some of which are named. But generally, they're just there to kind of collect the objects and make them more understandable. You don't want to have like all of that whole program be in one giant list. You want to be making it as hierarchical as you can so you can understand it. Sequences are a collection of objects in an ordered fashion. You can be putting statements probably and variables maybe in those sequences. Consider those the bodies of procedures many times. You'll be using those to build basic block graphs. Series of different statements would be collected into maybe a block in a general graph of a program's control flow. So let's see here. I got namespace would be like exactly the way you'd see it in C++, and then it's unordered, and then sequences are exactly what I described there. Okay. So objects and types are the next thing here. Objects are effectively instantiations of types. So they're things like variables, procedures, and registers. They're actual real things that you can reference in a program. They're things the CPU will see probably when it executes the program. They have the property that they all have types. So variables have a type. Procedures also have a type. Registers have a type, but it's generally pretty low level and basic and simple, like a span of bits, for example. Types are things like classes. The classes are a type of a variable. Prototypes would be the type of a procedure. Some languages like Ruby, you'll find it's kind of conflated, and that you'll find that the type system has a lot of meta information in it. Objective-C will also have meta classes, but they're also still just classes. So I use classes to represent those things. The concept is the same. The hierarchy here is that. Let's see if I have a better example on the next page here. This scopes, and then objects and types, and then procedures, variables, classes, prototypes. So basically, a prototype is the type of a procedure, and the class is the type of a variable. So that's sort of the way that the inheritance works in my IR. All right, let's see here. A span of bits here. I also represent, as I said earlier, low-level types using templates, and they have certain hierarchy like this. I'll take a set of operations like spans, and there'll be things like all the Boolean operators like or, XOR, not, that kind of thing. Things that you think are kind of int-like in nature, but they're not really. If you have a signed int or an unsigned int or whatever, an XOR operation, it doesn't really matter whether it's signed or unsigned. It doesn't matter that it's even an int. It's just a series of bits. So I make that the base of everything, because you can always do that to no matter what. And then you have the int operations, which are things like add and subtract and multiply. Turns out that multiply is actually an int operation. It's not a signed or an unsigned operation. This is a tricky one. I scratched my head over this for a minute. Divide is signed or unsigned, but multiply is not. The reason why is that if you look at the Intel CPU, you'll see that there's a signed multiply operator and unsigned multiply operator. Integer mul, imul, and mul. So why if there's two different multiplies, does it not pay attention to sign? The reason why is that it'll always produce the same result. In EAX, EDX, for example, you pass in some number in EAX, one in EDX, you multiply them together, you get something in EAX, EDX. It's always the same, even if it's imul or regular mul. What's different is the treatment of the flags. Carry flag, operators, overflow flag, sign flag, those kinds of things. The handling of flags is different between the two, but the actual operation of multiply is the same. You'll see that that's also the same reason why shift left in C doesn't imply any kind of type, but shift right does, because it determines whether or not you shift in a 0 or whether you carry the top bit when you do the shift. That carry is the sign implication that I'm talking about here. So divide, turns out, is signed or unsigned, but multiply is not. Good?
I'm a little confused, because earlier in your talk you said that you're not focusing very much on processor details, but abstracting above them. And the example that you just said is very into this is how Intel implements.
Yep, right. For example, but the idea that I'm getting at is that all operators, we're going to get to this in a second, but all operators at the low level, every processor, regardless of whether it's Intel or not, has many semantics. You're not just multiplying two numbers together. You're multiplying two numbers together and setting a bunch of flags and potentially, there's a bunch of other things that happen. And, if you pull apart, if you actually go get like the AMD or Intel, CPU manual, and you look at what those, opcodes do. Like you were writing a disassembler and you wanted to look at it, and they give you this system spec, and every operation has, maybe like this block of like 12 things that it does or whatever. At the low level processor level, you're going to be decompiling to that level. You're not going to be leaving out anything. If you leave out the carry flag, you're screwed. You have to do every little detail, or you will be missing out. You will not be able to go back later easily and just go put in a bunch of semantics. You have to note that when you're doing, say, an add of two things, that you have a lot of side effects, and that they're maybe sometimes not obvious. So just make sure that we're always reviewing those manuals when we do our initial disassembler. You're not disassembling to text. You're not just going to like add EAX, EDX. You have to really break it down into these actual IR operations. You're going to break it down into like maybe 9 statements that have expressions in them and all of that. And they do things like add and do sign extension, and then do a comparison and put that in CF, do another comparison, put that in OF, do another comparison and put that in SF, that kind of thing. Because at some point you're going to see some weird stuff, like somebody XORs two things together and then jumps on the parity flag. What the heck does that do? Maybe some weird compiler optimization maybe generated that code. If you're not going to get screwed up by some guy trying to insert weird operations that do funny things, you have to be able to handle every single semantic and get it right. So, we actually do that. If you see like a jump, on parity, we actually handle that correctly. So anyway, let's see. Variables are a high-level construct. The idea of a register is sort of the most basic thing that we initially maybe misunderstand. Registers are sort of a temporary location where a variable's lifetime may pass through. You may find that a variable at the high level, you say int x equals 3, then you do a bunch of things with x. It may be that the variable gets put in a register and then put in a stack variable and then back in a register and then pushed onto the stack and then
later on it's cleaned up or something like that. That whole lifetime of where the variable is located in memory, in the computer's memory, is sort of irrelevant to each individual place. You may have like 12 different places where that variable shows up, but they're all in fact the same they're just different representations of the same thing at the high level. So the low level representation would be each individual location, but the high level would be, the notion of the variable x, which should be conceptually free of any kind of low level representation. It's not like in C when you write int x equals 3 that you're saying, oh, and by the way, make sure you put this in edx and then put it in the stack, and then you're not saying any of that. The compiler worries about that, and then the decompiler also is going to worry about getting that transformation right. So I call that low-level thing that represents the variable's location at a particular spot its match expression. There's an expression like EAX or dereference of EAX plus 8 that represents the variable and where it's located at that time. I call that a match expression. We're going to use that term. So there are many kinds of match expressions. Global variables would be like dereference of constant number. Dereference of ESP plus 4 or whatever would be like a stack local variable. ESP minus 8 would be like a stack parameter. The dereference of a this expression of some sort plus 4 might be a member variable of a class that you're in. A multiple level deep member variable reference plus some offset, and maybe a VB table or VF table entry. I mean, there's many different kinds of things. FS colon whatever. Those are all ways of representing a variable at the low level that at the high level would look much more simple. Thread local storage, decal spec thread int x equals 4 would show up as FS colon, dereference of ESP plus some number. The other things that are low level, reasonably high level that we are trying to reconstruct are procedures. Procedures are functions, C and C++ functions, for example. They're the basic unit of interprocedural control flow, and they are effectively guaranteed to exist semantically by your compiler. So this is one of the things that we're going to be using to our advantage a lot. We're going to note that the output of a compiler is what I'm defining as the input to a decompiler for the time being. I'm not trying to handle arbitrary binaries, much like you wouldn't try to handle arbitrary text with your compiler for now. You don't feed the works of Shakespeare into a C++ compiler and expect it to do something. I wouldn't take an arbitrary bunch of bits and feed it into a decompiler and expect it to produce a meaningful program. So try to imagine a more simplified thing where the input has some rules that it's adhering to. The thing's got to run first off. The program, if it doesn't run, you don't care about it that much. If it runs, it has characteristics that make it run. It has things like it agrees that there will be stack conventions. There will be things like the ESP will be used as a stack thing, and then call and return at the low level will be used to move you around in the in a control flow call graph. So those things that we agree upon that the compiler guarantees to you are really important to know. If you don't use those to your advantage, you will not succeed in building what we build here. So anyway, procedures have the property that they're usually named, that they have a fixed or variable number of arguments or returns, that the arguments and returns to procedures are actually variables whose location is shared with that of the calling procedure. Note that the location is actually a match expression like we just described. This allows a call stack to share variables in what's called a frame. Frame is, let's say, your caller and then your callee. You have a certain amount that overlaps. You basically put a bunch of stuff into the frame, and you make your call and access stuff in your parent frame. So variables that exist in the caller, you're able to access through this interprocedural control flow process. ESP, generally, the stack pointer, is used many times, as well as registers and things to pass things, from one procedure to another. Go ahead.
So in the spirit of making your IR process a superset of all useful languages,
yep.
Do you sometimes run into additional details here when you're supporting maybe slightly more exotic things like closure and coroutines?
Yeah. Yep. If you wanted to represent those things, generally you'll find that the compiler's notion of a frame, for example, let's say we were looking at an Objective-C program, and it had a block being passed in or something like that, and that's actually like a lambda, which is a block of code that is kind of a free-floating entity. You find that the compiler actually represents those things many times as procedures at the low level. They'll just take a block of code, stick it over there, and they'll make a new block and say, here's an anonymous chunk of stuff, and we'll reference that. And what it'll do is it'll put the block's lambda closure context as an extra parameter in the a hidden parameter in the things in the argument list. So you'll have maybe in C++ the this object, if you would, the object that you are currently in, that you're a member of. There's a this parameter that's magically added by the compiler. That's not a closure context, it's an object context, but it's the same idea. A closure context would show up in the same way. C++, Objective-C would define that with what's called just a block descriptor object internally. And so you define that as a structure, say, that's a class. It has certain fields internally used by the Objective-C runtime, and you just make that the first parameter pointer to that, and you're done. So now you can represent that using the notion that the compiler is going to guarantee a certain representation. The Objective-C runtime has to actually run the program. That means that there's not a whole lot of different ways that can be represented. It's either one way or it's not. If you represent it some other way, it doesn't work. The runtime crashes and everything dies. So we're going to talk about variabilization in a little bit. Variabilization is the mechanism by which you take a low-level representation of a thing, all of those locations of a variable's, positions on the stack and whatnot, and turn them into a high-level variable notion. That also is the same time that we're going to discover what variables are used interprocedurally across a frame. So that's where you're going to find your arguments and your return values. Things that are used before they are defined are arguments, because they're defined in the caller frame. If you define something and then later on in the caller those things are used, downward exposed, if you would, then you're defining return values. So that process, I call it variabilization. It's the mechanism by which high-level things are discovered and reconstructed. Templates, again, I'll skip through this, but there's another lesson here. If you use, and I said before, that if you use templates to represent things like integer types, you can have int32 and int16 be different objects in your hierarchy, allowing for very specific precision without complex type selectors. Templates, you're going to have to support them. You just have to be able to understand what specialization means and what instantiation means and what the difference between a template in C++ and how it works and the notion of generics in Java. But you need to be able to support that. It's a little hairy sometimes. So a good IR should enable all of these things: data flow, control flow, various kinds of manipulation, serialization of this chunk, and debugging. So if you have like this whole thing that you've built, you need to be able to serialize it out to disk. You don't want to do a 36-hour decompilation, because this can take a while in a big program, and not be saving it out to disk occasionally. It'd be a bad idea if you couldn't just pick it up from where you left off. Data flow analysis is the heart of a lot of security analysis, so you're going to be wanting to enable that. Your variables are going to be the core of that, so being able to access those and understand what their contents are, their type information is going to be the most key part here. So just as a hint, DU graphs are kind of slow to create. They could be fast in some scenarios, but if you do a lot of creation of data flow graphs, you're going to find that that's suddenly the slowest part of your decompiler. So I'm finding that the best semantics here for me, the best way of doing it is to batch editing to your IR. If you're going to be recreating a DU graph all the time, if you're going to be modifying your intermediate representation, you're going to be updating that DU graph as you do it. If you do the updates too frequently, then you end up building your DU graph all the time and not doing your transformation. So the goal here is build your graphs, calculate as many operations as you're going to need to do in your transformations, and then commit them, and then go back and build your graphs again. But do as much as you can with the graphs you build. So DU kind of looks like this. Defs that are connected to uses. Multiple defs can go to multiple uses. Programs that are like x equals 3 if something, then x equals 4. Otherwise, continue and go y equals x plus 2. You'll see that whoops, back there. The definition of x here, the first definition of x equals 3 is, I don't know why it's clearing it, but is used later on, but then potentially conditionally it is redefined, and that definition could be also used at that same use spot. So that construction is and be able to do that efficiently is very important, and I'm not going to belabor that discussion too much. Control flow representation is important. It's important to have the concept of a program counter object, something you could like drop on an intermediate representation and say, okay, assuming that my CPU is executing an EIP is here, where can it go from here? Step forward, step back. Those kind of primitive operations are going to be key for generating control flow graphs. You're going to be able to say, okay, now step forward as much as you can, build sets, frontiers, those kinds of things. That cursor object is going to be important and is got to be able to work at low level and high level. So if you wanted to see the control flow graph for that, it's kind of what it looks like. In the interest of time, I am going to move on. Control flow graphs in general can get pretty complicated, but you have things like, this is going to be like, I don't know what I'm trying to do there. All right. So another lesson here is that one thing that's valuable here is that when you have a hierarchical representation of something and you're doing a bunch of transformations, if you have references that come in from the outside somewhere into the inside of a subtree, it makes that subtree very hard to manipulate. Okay, because you have to kind of fix up that incoming reference. You can't drop it on the floor. It's trying to talk to some object and saying, hey, I'm referring to this variable over here. If you eliminate that variable, we have to deal with that external reference. So one of the things that I've chosen with my representation is to make all expressions such that they cannot have external references to them. They can only have parent relationships. So in other words, a statement could have a bunch of expressions underneath it, but nothing can refer to those expressions. The expressions can refer outbound, but you can't refer inbound. It just makes it easier to transform expressions. That way you don't have to worry about fixing up stuff all the time. You have x plus 3. If something was referring to that object, you wouldn't be able to eliminate it if it was not used later, for example. So, that's kind of what I'm talking about. So, yeah, the problem here is like if I wanted to eliminate this, if I wanted to say, eliminate y out of this expression and just make it z equals 2 plus 3, I wouldn't be able to do it if something was referring to that x. It would be like, whoa, how do you fix it up? How do you do that? And you wouldn't be able to do it easily. So I'm going to skip over. Yep, sorry.
Making that design decision?
Yeah.
What was the consequence?
The consequence, by doing that, there's not a lot of times when you need to have an external reference like that, but just ensuring that it never happens allows you to make very straightforward transformations of expressions. But you really are going to be doing a lot of things like expression simplification. It's going to happen a lot. You're going to do forward substitution. You're going to be doing a lot of optimization. If you have external references, it just slows things down because you have to have sort of callbacks, if you would, on all your transformations.
Does that increase any of your resource usage or anything?
No. So the constraints of the real world, vector math, extreme use of templates, optimization, you're going to see it all. So be prepared to implement the entire Intel operating set, SSE3, you name it. Every little thing, you will see it. Even to pull apart a program of even moderate size these days, you're going to see everything that you could possibly see. I didn't handle a whole bunch of vector opcodes at one point, and couldn't handle analyzing Adobe Flash Player, that kind of thing. Couldn't do it. It took me a whole year because I had to go re-implement all this stuff that we hadn't done. So when we did it, suddenly we were able to start analyzing software like that. So, all right, at this point, I'm at the 1 hour mark, and we're going to get into the actual sort of the fun stuff. This is sort of the preface. It's going to get more complicated from now on. So if you want at all to grab any water or anything, that would be a great time. But if you don't, I'm just going to keep going. Okay. All right, go ahead. I'll give it like 2 minutes.
I like the Shakespeare analogy.
Oh, yeah. I try to be nice to people and let them hit the restroom just for 2 seconds,
Get bonus points for that.
Yeah. Don't worry, we're gonna get to some. There's gonna be pictures and stuff. It'll be happy in the next section. I got some demos of the thing actually transforming binaries, so I can actually look at some real world examples.
Cool.
A lot of fun. Don't worry about walking in front of the camera and whatnot. I'm just going to cut that part out later. So, no.
But if you make faces into the camera, yeah.
Well, I'm going to put that stuff right on YouTube. That's okay. All right, I'm just going to get started. Not everyone's back yet, but I'm just going to start anyway. So. All right. All set, guys? Okay, so the next lesson here is that compilers make assumptions. The assumptions that they make are absolutely essential to being able to perform the transformations. You need to know that things like the stack goes backwards on x86. I mean, those kinds of compiler and processor level assumptions are things that you need to know, and assertions, if you will, are things that you're going to need to know. You're going to need to understand those. That external functions follow a set of well-known calling conventions like standard call or fast call or cdecl. Those mechanisms where that's parameters are passed on the stack and not in registers, and then returned in EAX and pointers in EAX for structures and things like that. The actual object model and the parameter passing model for the compiler is going to be extremely useful. Note that you can't apply random assumptions all over the place. You have to use them where the compiler used them. Things like the declaration of a function calling convention for an external function does not apply to an internal function. Something like a static function that is only used inside a particular translation unit. The compiler has the right to optimize its calling convention and do whatever it wants. It can pass a parameter in EBP. And you never see that, but you do. You don't think about it, but you see that when you look at what the compiler has the right to do. The contract that it has with the world is only that the compiler has made rules for external functions. It has absolutely no rules for some of the internal ones. So, inputs for the modeler. Effectively, the modeler takes in executables, linked libraries, environments, debug symbols. I already did. Thank you. If any of these inputs that are required are missing, you're going to be sacrificing the readability of the output. So if you, for example, have an executable that links in several DLLs and one of them is missing, you're going to be like, okay, what is this thing? What is this place I'm calling into? What happens when I call into it? So you really have to make sure you have everything. So environments are the notion of an edge of like what you care about. Note that the compiler compiles your program and links it up against a bunch of other stuff that comes from the operating system. You didn't write the Windows kernel, but your program links it in. You might have, but if you've written maybe 20% of your program and linked in another 80%, there's this field of stuff that we care about when we're decompiling. We may not want to decompile beyond that realm. There's that edge. Now that edge, if you're going to stop decompiling at that edge, you need to have type information on that edge. much like the compiler couldn't link in a DLL with a function like create file or whatever without linking in windows.h and all of its appropriate bits. You really can't do the same in a decompiler without having some type information on the edge so that you know where to stop and then what it means to stop at that point. Good?
So doesn't this really complicate data flow analysis?
Yes.
Saying,
You bet.
I'm putting this boundary here because here we track the kernel.
Yes.
And the kernel's going to change my state in an unknown way.
That's correct. So for data flow analysis, if you were going to do, say, a security analysis, and your control flow or data flow goes off into space, and you're like, whoop, you have to have some kind of concept of what the data flow, like maybe a summary or some understanding of what that data flow is, so that you can understand maybe if it comes back into your programs through some other means or whatever. At Veracode, one of the things we've done is we've actually gone through and analyzed all of the things that you link in. So we actually have models, and for the things that you can't analyze or things that cross into the kernel, for example, we actually have manually added enough information that programs can be analyzed all the way, and we have basically complete data flow for things that you don't analyze 100%. So if you're analyzing Java frameworks like Spring or whatever, or Hibernate or whatever, and you have written your program to use those things, we need to have models for those frameworks too. Turns out to be like the major problem for static analysis is actually making sure that all of the frameworks have the proper data flow information associated with them in their environment. So basically we take these frameworks and these extra things that we don't decompile, and we make environment files that have this DU and data flow information in them. By actually generate them by passing them through the decompiler actually, and then having scripts that analyze those things. So it ends up we need to generate that stuff. Again, we're not really going into the process of DU analysis and security analysis, but in the actual decompilation pipeline kind of doesn't care what happens on the other side of the environment barrier. Anything could happen over there. It just doesn't matter to the compiler when it's making your program and it calls create file. It doesn't matter how create file works. That's the whole point, right? So you really don't need to know for the decompilation part, but you do need to know for the analysis part. This is why decompilation is totally possible, but an analysis of arbitrary programs might eventually reach halting problem levels. So you do have that. Environment compilation basically looks like this for MSVC. You build a list of DLLs, find all the header files that the compiler would use to link all those things into your code, and then you compile the header files into your IR format. You actually have to build a C++ compiler. Good luck. Take all of VM, for example. Make it output your IR format. Don't write your own C++ compiler from scratch. You spend all year doing that instead. All decade doing that instead. So then you end up pairing up the objects that are in the DLL's exports by signature. So effectively you demangle the object exports and line them up with the IR stuff that you compiled from the headers. So if you have like some weird mangled name or an external name like underscore fprintf, you can take that, search for it in the IR tree, find it, and be able to pair up the exported address of the DLL with the actual IR object. Now you can put those things together, and anytime you see a call to fprintf, you know that there's an IR object that you could be calling instead. That's the kind of thing that we're looking to do. If you have a C++ class that you're calling, some standard library function, some std allocator, yada yada, that will have some funky mangled name. You have to make sure you understand how to parse that mangled name format and reverse it. Undname does that. C++ built does that. You're going to build one that does that and actually can create IR objects or search through them if they don't exist, or if they exist already. Be able to search and find that particular function and then match them up. That's a lot of reverse engineering because it's not documented, but it's not hard to do, turns out. Modeling pipeline. Front-end environment loader, data flow transformation, data flow optimization, control flow transformation, and then optionally some source generation. So the first part, the front end, is going to be platform and compiler specific. The optional back-end source generation you'll find is going to be language specific. You may want to be able to take something in that was initially manage C++ program and decompile it to C#. You know, there's no reason why I couldn't do that because the transformation makes sense and it goes through a common SIL representation. So let's see here. Platform-specific front-end loader. I was talking about this demangler here. This is the kind of thing that you're going to end up parsing, finding objects. You're going to end up finding that there's type information in a lot of weird places. Export tables, RTTI information, symbol tables, mangled names, things that you have from Objective-C, runtime information, you know, whatever. You know, some languages require a whole lot of extra type information, some have none. So whatever you can get your hands on, make sure you can transform those things at the front end into the IR. Take all as much type information as you can. You'll want it later. Data flow transformation. I'm just going to skip right past front end because for the most part, it's just loading up a whole bunch of stuff that's well documented. If you can, you know, load up a PDB file and make IR objects out of it, go ahead and do that. It's a good idea. RTTI, also documented through various reverse engineers out there. I'm going to go into how that works. Just know that you have to make IR from that. The data flow transformation process is the beginning of the hardest part here. You're going to be importing, in other words, decoding and disassembling opcodes, variabilizing them, propagating them, merging them, and then doing more code discovery. At that point, you can do things like call conversion, making low-level calls turn into high-level expressions, and then do things like reference conversion because you will have discovered all the variables in the program at that point. You can then say, without a doubt, that ESP plus 8 at a particular point refers to a particular variable. So, you know, it's the dereference of ESP plus 8 would be the variable, but ESP plus 8 would be the reference to that variable. Knowing that that's a reference to the variable and not just some other calculation happening that's part of some other thing is really important. You have to know that the variable's there before you can call that ESP plus 8 a reference to it. So dealing with things like address of variable, you do that after you've discovered all the variables. That's how it works. Okay, so import. You iteratively decode instructions from places where you've determined the instruction pointer can reach. Specifically, we're going to start with entry points, and then you're going to build basic block graphs connecting all the well-known control flow into a basic block graph and a procedure graph. This will not find all the code, as I mentioned. Indirect control flows, such as jumping to registers and memory references, cannot be easily sussed out until later in the process. You're just going to be decoding everything until you find that you can't go any further. And then you have basically the first part of what you're going to transform. So now you're going to end up with a whole bunch of opcodes, and they're going to turn into your internal representation. So, move on here. Variabilization is the process by which real variables are created to represent low-level register and memory accesses. So, we start doing this by creating a whole variable, an actual high-level variable for every single def use site. You know, until I've told you otherwise, if you say EAX equals 3, and then EBX equals 4, you got two variables there. Okay. If maybe later down the road you see that somebody says ECX equals EBX. Okay, well, is it the same EBX as the one that was defined before? That was a question. Or is it a different EBX, potentially? What references to EBX are that high-level variable? So what we end up doing is we use DU to solve this problem. We end up finding all those definitions and we propagate them forward to find all the uses that they reach. So if you do that, you can find all of the different things that potentially are a particular variable. So let's see. If you look here, proc_foo, there's a site here. I'm going to call this site basically a variable reference. You have a site for ESP. You have a site for EAX. You have a site here, a site here, a site here, a site here, and then a site here. There's a site for EAX, but also a site for dereference of EAX. Because both of those are actually references to variables. Dereference of EAX could be, if you look at it, it's dereference of ESP plus 16, which is actually a local variable. So the notion of a stack variable, you have to first have found that EAX here is a variable, and then you use that, and the larger variable that it depends on, if you would, is the dereference of that. So what you end up with is references in the match expression of the higher level variable. So if you have a stack variable at ESP plus 16, that actually, the ESP has a site in it. And that's the site. It's in the match expression of the variable. So, the representation of the variable at this point matters. Let's see here. Just try to make this a little more clear. So the variables are references there. Okay, those are defs and uses. So there's a def of EAX in red there, def in EBX. And then use, and use. Okay. So variabilizing stack variables. The trick here is to measure that all of the allocated variables that are on the stack with reference to the base of the stack frame, which is effectively the ESP at the entry point of the procedure. So the base of the stack frame is going to be that of what the value of ESP is at the top of the program, at the top of the function. That may move around as you do pushes and pops and things. And people sometimes use frame pointers, EBP equals ESP at the top at the function prologue. But if you rely on that EBP to be there, you're going to find that you're screwed when you realize that optimized programs don't have those things. But they always do have an ESP at the top of the procedure. That's always there. It's guaranteed to be there. So if you make your match expressions based off of the ESP at the top of the procedure, you're going to be in win mode. So what you end up doing is use basically forward step substitute, and you use range propagation to figure out what the ESP is, the offset is from the ESP at the top of the procedure at any particular dereference. So if I see ESP plus 8 dereferenced, it matters where in the program it is and what the value, the offset of ESP is from the ESP at the top of the procedure. If you've moved it around a whole bunch with pops and pushes, you're going to find that it's not really ESP plus 8, it was actually ESP plus 16 if it was ESP at the top of the procedure. Right? That builds your frame. The frame is the notion that your ESP kind of centers you in the world at the top of the procedure, and that everything else, all the motion that the stack does, you track that, and then when you have your dereferences, you can keep track of really where you're looking at inside your frame. The compiler's not going to do the tricky thing, which is to take a single dereference of ESP plus 8, for example, and have it refer to two completely different variables depending on how you get there control flow-wise. So I'm not going to do that. The variable's always going to be the same variable, doesn't matter how you get there. So you could probably manually hand write a program in which that still did something meaningful, but it doesn't happen. Compiler's not going to generate that. So for now, we're just going to assume, and we're going to assume because the compiler assumed that that's going to always be the case. That offset is going to be site specific. So yeah, let's see an example there. But ESP, there are sites for ESP, and you can see here that the sites for parameters to A are things like ESP minus 4 dereferenced, ESP minus 8 dereferenced. There are sites here for ESP. That's a parameter, and that the stack, it can move around. If you wanted to refer to a particular variable, it could be through EBP, it could be through ESP directly. It really doesn't matter. But the one thing to note here is that these are the match expressions for these variables. Eventually, the goal of this whole process is going to be to eliminate match expressions. The reason why is this is a reference to this. And that in a real high-level program, when was the last time you ever saw foo and then parentheses, and then some passing in ESP to it. You don't do that. Compiler does that implicitly. It's kind of passing it in as part of the calling convention. But you don't really do it. It's not like it's really there. But you can't ignore the fact that that's what's happening at the low level. At the high level, you don't want to see it. Now, how do you not make that go away is the question. How do you make that whole frame disappear? Is by saying that the match expression's no longer necessary. Once you can eliminate the match expressions from your variables, then you're not going to refer to that top ESP at the top of the procedure. And then you can eliminate it as part of your optimization process. So, we'll get to that. Propagation and merging. The goal of variabilization is to create as many variables as necessary to represent correct data flow, but no more than that if possible. We start by creating many variable sites and then propagating definitions downward through the control flow graph, where they meet overlapping match expressions on use sites. Then we merge the two variables together. This is similar to single static assignment form. But instead of that, we actually have a thing called single constant assignment form. And effectively, instead of inserting 5 functions, and I'm going to skip through some of the theory here, but we actually do this operation called the merge. Anytime a variable that is, say, overlaps in lifetime, we merge it together and they become the same variable. They must exist. They must be the same variable if they overlap. So the propagation process is sort of a frontier propagation where you build a set of things that are downward facing for definitions, a set of things that are upward facing, and we propagate them together until they meet. The things that meet at different positions on the stack merge together. So for every site, we initially start with a variable for that site. So if you've got ESP up here, or sorry, EAX up here and EAX down here, they're different variables until we prove by propagating them up that they meet, that they have the same value at some point in the program's execution, that they are in fact the same variable. Then you merge the variables together, and now you have 2 sites for the same variable. This is a monotonically increasing process. You always merge, you never unmerge. Once you've merged, you're always going to be merged together. Go ahead. Somewhere else, right?
That's where you would just take what the EAX equals at that point and just forget about everything else prior to that.
Right. Well, what happens? Okay, let's add another definition here. No pun intended. When you define a variable, it also kills any other previous variables in that same location on the stack, for example, or in the frame that you're in, or at that match expression, effectively. So. If there was EAX equals 3, and then you say EAX equals 4, the second EAX equals 4 kills the first EAX equals 3. That one doesn't reach past it. It's only the EAX 4 that gets to reach downward. So when you're doing your propagation downward, you keep a set of live bits. And then when you have a definition, maybe of 16 bits of a register, now you've got 32 bits, EAX equals 3. And then let's say, do AX equals 4. Uh-oh. Now, what does that mean? It means that you know that the top 16 bits are actually the first variable and the low 16 bits are the second variable. So you have to be able to keep that down to the bit level. And when you're doing your propagations, you're tracking them by on the bit level. So if you were, in your example, if you have a comparator, and I say, if X is less than 3, then Y equals 2. And previously, there was a Y equals 1. And then later at the bottom, I see X equals Y. All those Y's are the same because you have 2 definitions that reach a single use. They both intersect over different control flow paths. And then they merge together and they become the same variable. So that notion of kill is also very important in the build in the propagator that does this def use propagation. All right, so SSA versus SCA. SSA form, for anybody that's seen it, looks like this. You find lifetimes that overlap like this, and in places where they diverge in control flow, you insert a 5 function that represents a transition between, potentially going this way versus going this way. Now, that phi function is actually a merge in my world. And in this SCA world, we actually just make it all one big happy blob. We don't keep that phi function around saying, that the fact that there's control flow involved doesn't matter to the compiler. You're not trying to keep the control flow around. You're just trying to say all of this is one variable. Any questions? Okay. All right, so now there's two kinds of propagation that we're going to be worrying about: intra-procedural propagation and inter-procedural propagation. Intra-procedural is the idea that you have some defs and some uses inside a procedure, and that you maybe walk the defs forward and the uses upward, and they meet each other, and what we were just talking about. Inter-procedural propagation is the idea that arguments, like maybe some things, you have uses of like EAX, for example. You use EAX, and you walk it upward, and it reaches the top of the procedure. Now where do you go, right? You have to walk up to all the places where that procedure is called. So you walk in the control flow graph of the entire program to the next procedure and to all of those call sites. And you end up propagating to all of the different places where that procedure is called. So the idea that EAX is used before it's defined makes it upward exposed in the program, in the procedure. And then it'll meet a definition at the call site of EAX. So you'll say EAX equals 3, call foo. Inside foo, you'll say something equals EAX. And those things will meet each other over the call boundary. This is really straightforward for registers, but it's not so straightforward for things like procedure calls for stack variables. You're going to find that the stack's location, the offset of ESP matters, because the variable that you're looking at is going to be potentially defined in the frame of the caller at a different offset for every different call site. So you have to be able to do that same ESP offset calculation when you just do this. It's called a frame translation. You have a variable in your called procedure, and when you propagate it upward, dereference of ESP plus 8, you propagate that upward, and then maybe, or ESP minus 8, if it's a procedure parameter. You propagate that upward, but maybe it's not ESP minus 8 in the caller, obviously. It could be like, ESP plus 160. So doing that frame translation means that you're translating from the call ESP to the caller ESP. So that's the only difference, is that you have to be able to translate cross-frame boundaries. This involves range propagation and doing a substitution and an arithmetic simplification for all of the different match expressions, for all the variables that you're propagating from one frame to another. So when things merge interprocedurally, they become arguments or return values. Now this could happen over the course of multiple call level depths. You could have something used in a procedure, and then upward exposed, and through its caller, upward exposed again without even being defined into the next caller. You define something, it could be passed, theoretically, it can be defined here, and then a couple procedures down in the call stack, it can be used. And then it suddenly becomes a variable in all of those frames as it propagates. So, basically it's this. All right. So, note that this is just basically a whole lot of propagation and a whole lot of frame translation and a whole lot of expression simplification and substitution and propagation again. I mean, it's all it is. Just gonna kind of breeze through this a little bit so I can get to some of the more fun parts and make sure I have time for questions. Code discovery is what you end up doing after all of this is done. You've built a higher level representation of variables and all of that. You can actually, at this point, also do a whole lot of type reconstruction and sort of more useful things like structure reconstruction. And at this point, you've got high-level stuff that's high enough to be able to do that. You're going to see indirect jumps that are going to turn into switch statements most of the time. These are idiomatic. They'll basically be like 3 or 4 different table-based ways that switch statements are constructed. It'll have, maybe 3 or 4 different ways compiler does it. Study that and make sure that you have a way of representing it. You're going to see that the dereference of EAX is actually EAX, which is a global variable, which is actually inside a procedure, and you can see that it's a table of functions, and that it's preceded by a jump that's if EAX is greater than 10 and basically less than 100, then dereference this table. That's like one way that a switch statement would be represented. That kind of transformation is idiomatic in nature. The compiler just has a certain number of ways that it's going to do it. Things like inlining memcopy and string copy and things like that, those are also idiomatic in nature. There's only so many different ways that it's going to do that too. You're going to end up finding that you idiomatically deal with a lot of the compiler's ways that it represents things, and then you end up doing those kinds of transformations and code discovery, for example, idiomatically quite often. But the things that are not idiomatic are things like variabilization, because the compiler has the right to optimize and lay out the program's procedures in any way that it wants. So another thing here is that when you're dealing with things like virtual functions, that the compiler didn't know where virtual functions were going when it built the binary. You don't have to know where the calls are going either when you're doing the decompilation. You may need to know where they're going during an analysis, but not during decompilation. You just need to know how they go there. So we have you need to know the function prototype, actually, of a call. You don't necessarily need to know the target of a virtual function call. For example, if I wrote an executable, I can make a DLL 20 years later that it calls, that does the allocation of an object in virtual function table and all that. The executable can be built and work perfectly, and the DLL can be the one that actually determines where the control flow goes in the executable. It can be written 20 years apart, and the compiler just has a certain contract. It says, well, if you're going to call that function, it's going to be an external function calling convention. It's going to work this way, and magically 20 years later, everyone's going to agree, and it's going to work, and it does. So, call conventions, call conversions are the process by which you take all the call statements and turn them into operation expressions. Basically, all of those things that propagated into procedurally, you can turn them into prototype types. And then you can create operation expressions for all of the call statements that actually have arguments rather than simply just having variables, floating around like EAX equals 3 and then call function. It'll actually be that EAX propagates into the prototype of the function call. And then you can just hook that up and just say it's actually foo of 3, for example. So, like that. Okay? Looks like that. So that's a call conversion right there. Reference conversion is the process by which you have a complex expression, like the address of a, array index 100.b, array index 2.c. And then it starts off life as a reference inside of A, such as like dereference of address of A plus 812. Okay? It's actually, you're walking the type information hierarchy for the type of A in order to figure out what that plus 812 really meant. And that high-level representation comes from knowing the type information. So you can use a range propagator there. You can do a bunch of substitution, and then you can note that ESP plus 12 plus 812 is the reference of A. So if you get that procedure, you get this function here, this expression, you get that as address of A. And then some other thing over here, like that. Some offset. So I'm going to skip that. Type voting is more propagation. The idea that that there are loose types in the system. If you have just like a register, EAX equals 3, you don't know what type EAX is. If you say EAX equals some variable, then you kind of want to type EAX to be the same as that variable, or at least a little bit. You can say that that's a vote, that EAX should be the same type as that variable. If you know the type of the variable, then you know what EAX kind of should be. Another way of saying is that you're trying to eliminate casts in the system. There should be as few casts as possible. So the goal of a type voting system is to balance the types for loose variables that don't have real types of their own, so that they minimize the number of types in the system. Sorry, minimize the number of casts in the system. You're trying to avoid having to insert casts all over the place to make types coherent in expressions. So I'm not going to belabor that one too much. So yeah, if here B and C are potentially a signed int or an unsigned int, and then you're doing an int operator, what does that say about A? Is it signed or is it unsigned? You don't really know. You just know that it's an int, at least. But if the operator was a multiply, well, then I guess it's an int too. But if it was a divide, then it would have to be a signed divide or an unsigned divide. There's no such thing as just a divide. It's one or the other. So at that point, you'd be picking. At which point, if you picked signed, you'd be dividing a signed number from an unsigned number, and you'd have to insert some kind of thing over here. It turns out that at that point, you'd have to insert a cast here, but that you could make A a signed integer. So let's get past that. How that works is an exercise left for the reader. So data flow optimizations. We're going to breeze through this a little bit, then I'm going to give some demos of this thing actually working. I've done some recordings of the software that I've written on my desktop, and we're going to pull apart some programs and actually look at the model. Aggregation, match expression removal, copy constant propagation, expression forwarding, algebraic simplification, dead code elimination, unused variable elimination, variable merging, and idiomatic pattern replacement are all things that are reasonably well defined in program transformation theory today. If you were to go out and search for copy constant propagation, you'd find like 8 different papers on it. I'm not going to belabor this. Read the papers. They're good, useful kinds of things to do. All of those are very valuable. Aggregation, just roughly, is the mechanism by which you find member accesses in type information. So how do you know, by the way, if you are referencing the first member of a type or referencing the whole type? Open problem. Match expression removal. At some point, you're going to end up removing the match expressions from variables. After you've merged them all together, you'll find that you have merged together a whole bunch of different variable match expressions. It doesn't make sense anymore that the variables have different, like maybe 12 different match expressions over the lifetime of the variable. You just eliminate them at that point. You say, yep, now it doesn't matter. And once you've done that, you end up finding that you've eliminated the references to low-level constructs like the stack pointer. You can eliminate the actual stack pointer references in the intermediate representation at that point too, and the whole program becomes simpler. Now it looks high level. So let's get past that. Expression forwarding is literally the forward substitution. Not going to get into that, but it's just algebraic forward substitution. Algebraic simplification. If you have like a plus 1 plus 1 plus 1 plus 1, make it a plus 4. This is not really hard to understand. The one valuable lesson here is that you should pick a canonical representation. It should not turn into 1 plus a if it can turn into a plus 1 all the time. Just, if that's a plus 1, it's a plus, it's a plus 1. Don't make 2 different possible outputs for your simplification. Make sure that you pick a canonical representation for all your expressions. It makes it really easy to do just a tree walk to compare 2 expressions and determine whether or not they're equivalent or not. Otherwise, you end up doing a whole lot of, you end up building an expression comparator that does things like, the distributed properties and associative and all of that, commutative. You're going to end up doing that stuff anyway, but the less of it you have to do, the more obvious it is when you just want to compare 2 expressions. So, variable merging, we've already talked about that. There are numerous other ways of merging variables after optimization as well. If you determined that really there's no reason, after you've eliminated your match expressions, if you just say A equals B, and that's the last time you've ever heard of B, then maybe you could just put them together and just say that they're all the same variable, just make all B's A's and call it good. So, again, pattern replacements, you're going to find 32-bit arithmetic done as 32-bit chunks, unrolled block copies, inline functions, architecture-specific patterns, complex comparisons, floating point comparisons, dividing by powers of 2, Language-specific patterns like new and delete and constructors and destructors, allocate, static cast through virtual bases, and exception handling. I mean, those kinds of things are all things that the compiler does in an idiomatic way. It will do it a particular way, and you'll see it. It'll look a particular way, and you'll be able to say, "Oh, that thing, that's an exception handling," and you just simply replace the low-level representation with throw. So you see, the stack frame getting set up on fs colon whatever. That is going to always be the same way. It's going to be guaranteed that those things are done in a predictable fashion. So, control flow transformation, I'm just going to breeze through this, but the idea is that you're going to do interval analysis. Interval analysis is well-documented program theory. I recommend Christina Cifuentes' thesis on the subject. She wrote a thing back in 1994 that was a 16-bit x86 decompiler that had a really good control flow transformer. It didn't do much for data flow, but it did a great job for control flow. It didn't really have a variabilizer or anything like that. But it did a really good job finding if statements and while loops and switch statements and all of that. So building those high-level things from the low-level jumps and whatnot are really the job of this thing. So you end up with this. You have these different reducible intervals. This is what they look like. Like that would be like a conditional. This thing's a loop. That's a conditional with no else. A switch, an exit, or a break, or cycle. So you can think of an interval as a node in a control flow graph. An interval is the maximal single entry subgraph in which H is the only entry node in which all control flow closed paths contain H. So that H at the top is the header node, and then you walk forward. Every control flow thing that goes through that and is completely closed is an interval, and it kind of looks like this. Okay, so if you have a control flow graph that looks like this would be the first interval, and this would be the second interval. This is a head node, that's a head node. And effectively, you can start thinking of those things as like what you're going to turn into your curly braces in your program. Okay, those things are going to be hierarchical. Intervals are reducible. This is actually a graph that's simpler. It looks like this. So here's that same graph. Okay, and there's that same interval. And now the second level of interval graph now looks like this. And then you can just keep reducing it until you have the top of the program. So this could be like the brackets that are the outside of your program, and then here's another pair of brackets here, and then there's another two pairs of brackets. All right. So once you've determined how to look at your graph that way in a hierarchical fashion, build G0, and from that build G1 through simplification and collapsing of the nodes, you can build all the way down until you've reduced your graph down to one node. And then you've got all of what you need to do a high-level control flow transformation. So these are all of those kind of crazy-looking things. There's multi-level cycles and exits as well. So like break right in C only breaks out of one level of loop. But you can think of break 2, where you break out of multiple levels of loop. It would be a multi-level exit. Those kinds of semantics may not be representable in every language. You couldn't do break 2 in C. You just can't. You can do it with goto, but it's not as a break. So it gets complicated. There's a lot of weird edge cases here. Compiler does a lot of crazy things behind your back, and you end up with a lot of strange-looking stuff. Imagine a program that has an if statement inside of a while loop, inside of a for statement, inside of another if statement, and then inside of all of that there's a return. And then inside of some other else statement there's a throw. Uh-oh, now it's starting to get weird. It's starting to get really hairy. You got to keep track of all that, and this control flow transformer makes it kind of hard to build. Turns out that exception handling is something you want to do at the data flow stage, not at the control flow stage. If you haven't done it by now, if you haven't handled it at least a little bit, then it's going to be hard to transform it properly. you kind of want to think of it like a go-to that goes off into space by the time you get to the control flow transformer. Like a throw that goes off into space. There you go. That's the way the compiler's thinking about it too. So that's the end of the slideshow. I'm just going to throw a couple demos up, and I'm going to talk about them if you like. I'm going to skip past some of the junk here, but this is my, let's see if I can do this full screen. This is my desktop at the office, running a program called Charlotte. Charlotte is a Windows web server. It's very, very simple. The source code looks like this. It has, very simple structures. It's a single C++, file. And it calls a bunch of Win32 stuff and a bunch of standard library stuff. You can see, network code there. You can see multiple levels of for loops and things. This is the original code. This isn't the decompiled code. But you can see what it looks like there. It's got multiple levels of things like variadic function calls and things like that. So we feed this thing into this tool, and just open the executable, and here you go. You'll see here that it has detected the environment. And notice that it's linking a bunch of Windows Win32 stuff. There you go. And it kicks off this process of parsing the environment files, which we've already built. There's a front end it's going through now, where it loads up, say, the stuff for the WinXP kernel, which is all of the different Win32 API stuff. It creates environment objects for those, and it starts loading the PDB file, which we may have for this. If we don't, we don't, but if we do, we do. It parses the line number information if it has it, which is useful for reporting back any flaws that you might find. And then saves those objects out. This is us checkpointing to disk so that we can serialize it back if things crap out. Then it goes back into variabilization. We're immediately starting with propagation. Local code discovery. It's moving awful fast, but you can see that it's blowing through all this propagation. It does a bunch of replacements on variables that it's discovered, and starts building ref sites for reference conversion. It freezes the variables, does the call conversions, type voting, reference conversion, and then when it's done with that, you have basically done the data flow transformation, finalizes exception handling, saves the objects out, moves on to control flow, blows through that very quickly. Actually, it's going to do optimization. It's going to do type voting. It's going to do optimization. It's going to do all that expression manipulation. You can see it plows through all of this stuff, including things that come from standard library, ref and deref conversions, optimizations, renaming of objects. It tries to intelligently name things that it has debug symbols for. So if it has like some variable that's used in a loop, it tries to name it I, stuff like that. Well, it looks nice and readable when it comes out. If it has some variable based off of the type, let's say it's a string, you might name the variable a string or string1 if it doesn't have a piece of type information for it. At this point, it's done the control flow transformation. It blew through 194 procedures in the time that you were staring at it, and it's running the backend now, generating source code, and here it is. And there we go. Come on. This is what it looks like. That's the source code that we've generated, not the source code that we passed in. And that's straight C++. So you can see that it's got multi-levels of control flow. It's got correct variables. You don't see any low-level semantics at all. It's a complete and total reverse engineering of the program. So you can see that it's very familiar looking. It almost looks exactly like the initial input. It's got the hierarchical stuff for the control flow. You can see that it's made some certain decisions on type information that might be different, but it's got hierarchical, aggregated type information based off of types, can see that we've even gotten the multiple levels of variadic function stuff working correctly. You have to do some really weird things with variadic functions. You can have a printf that returns into another printf. So then what happens to all the parameters? Like which parameters are going to which printf? You know, printf returns an int or whatever, right? Or printf returns an int, whatever. What if that goes into another printf as an argument? Now how do you know which parameters are which? Anyway, so this is an example of a C++ program getting pulled apart. Let's see here. All of the different parameters there. That's actually a function call that returns into a variadic function. And that's all done correctly. You can see the C++ stuff here going on with the operator shift left. Minor details. That's something Veracode inserts for our own taint propagation and our analysis. We actually get the right to insert random stuff into code when we analyze it, so it helps us later on when we do our own checks. We say, hey, look at that thing. It's an interesting function, you know. So that's what it looks like. Thanks. I've got a few other short ones. I'll just skip to the fun parts, but this one is full screen. This one is a tool called Tor Proxy. It's an Android APK file. So we just open the APK file directly. You'll see here that it kind of looks, this is Tor Java. You'll see this is a Java program. And this is what the initial input program looks like. So it's kind of straightforward. I'm going to go ahead and hit go. And I'm going to actually plow through the transformation process because it's not that interesting. But you'll see that it does basically the same thing as C++. It skips past the variabilization process for the most part because it's really straightforward with Java. It's really easy. You don't need to spend all this extra time figuring out what's what. You know exactly what variables are where. It's like, it's right there. So let's see if I can just move to a better part. Optimization. And saving on optimization. Okay, so then there's the back end. Okay. And for this program, yeah, this is actually not just regular Java, it is in fact Dalvik. So we have a specific Dalvik importer that is directly decoding Dalvik instead of the standard JVM instructions. So this analysis complete. It's going to pull it up in a second. And you'll see that it looks eerily familiar. Okay, so also, this is that hierarchy. You can see the namespaces for Java. You can open those up. You can see that there's a namespace for activity.class. You can scroll down. You can see the constructors and all of the different procedures. Those actually, that's the IR that we use. And we're talking about all that stuff is all visualizable here. You can debug it pretty easily. Everything's got its own individual ID. Everything's uniquely identifiable. And we don't leave anything out. There's a unique ID for every single object. All right, so if I go all the way down into crypto digest, take a look at a function, you'll see that looks like that. Pretty straightforward. That's the class. And then if you, let's say, move on a little bit here, just kind of kick it over a little bit. Yeah, this is what some of the code would look like. See, it's pretty clean. You can see that the control flow transformation had, handled the exceptions and all of that. So this is what that Tor class looks like. So you can see it does the exception handling there. It's got the tries, got the catches, multi-levels of that. A try inside a while loop with multiple levels of catch. So you'll see there that it's a complex conditional with an AND statement, with a catch inside it and a return inside the catch. So it's all pretty complicated from a control flow standpoint, but it handles it completely. It's a try with a while, with another try inside it, with an if statement and a return. So you can see that it does the whole thing. And then constructs variables with a new, multiple levels of that. So yeah, that's what that looks like. So, and the last one that I'll do, real quick. What do you mean?
Like, what do you guys use it for primarily?
We take it in and we hit another button which scans it and returns an XML list of results. In fact, we don't have human beings do this at all. In fact, we don't generate source code at all on any production customer binaries. I gotta say that. Executables come in. What do we look for?
What are you looking for?
Find it, buffer overflows, SQL injections. I mean, all the OS top 10 and sans top 25 type stuff. We actually have all of this running in a facility that human beings don't even enter. The binaries come into this facility, are only decrypted briefly for a short time, are analyzed, and an XML turd pops out, goes to our platform, and is delivered to the customer in a nice PDF. That is done without any human intervention, which is the whole point. If we were to actually be looking at these things, it would be a huge violation of our customers' trust, so we don't do that. In fact, we make that part of our contract that we're never going to look at their stuff. The decompilation process generates something machine-readable that generates their results without actually generating the source code, because it never has to. Just looks at the IR, generates the results, and moves on. We have to be pretty sensitive to that. That's the number one thing we're concerned about, is the safety of those things. So what I'm feeding in here into this run, and I'll let you go, is a managed C++ program for .NET. And we're going to decompile it to C# instead of the managed C++. So the input looks like this. Just show you the input real quick. Let's see if I can find it. All right, well, I'm just going to hit go because it's okay. This is the input program. Is the input stuff written in managed C++. You can see the handles and the GC new and all of that stuff. And then the decompilation looks like this. And it looks suspiciously like C# instead of managed C++. It means the same thing, but it is syntactically different. It shows that it doesn't have to be exactly the same language that you're generating. It's an IR that you're forming, and then you represent it any way you'd like. So anyway, that's it. Thanks, guys. If you have any questions, you can talk to me at lunch.